Okay, thank you for a warm introduction. Hi everyone. Today, as Mark said, we want to talk about possible attack vectors on quantum computers. My name is Adrian Coleșa. I'm an assistant professor at Technical University in Cluj-Napoca and filling a position as senior researcher, security researcher with Defender. And here is my colleague Sorin, Boloș, who is co-founder at Transylvania Quantum and engineer the same company. We are coming from Romania. We are coming from Cluj-Napoca, city in Transylvania region, which is precisely the Transylvania I've heard about in relation with Dracula. Still, our talk is not about Dracula at all, not even about Dracula and quantum computers. But it is about a group of researchers at Bitdefender and Transylvania Quantum, so it's not only about two of us, which are present today here, who investigated, analyzed the relationship between quantum computers and cybersecurity. In particular, we wanted to ask the question how vulnerable are quantum computers? This is because typically quantum computers were seen and are seen maybe as possible weapons to break classical cryptography. But another perspective often ignored is that quantum computers themselves could be attacks. So our purpose was to investigate this problem. Which are the possible threat models, attack vectors on the quantum computers? We focused on some popular quantum software development kits, in particular Qiskit. We also looked at some popular quantum providers, in particular IBM and IonQ, which fortunately for us provide free access to their resources. Still, our finding is not necessarily particular only to those SDK and quantum providers. Okay, before delving into details of our investigation, let's try to briefly review some basic concepts regarding quantum computers, because we need them to be very clear for everyone in our later presentation. Because Sorin is our quantum expert, I will pass the floor to him to let us introduce in this concept of quantum computers. Sorin, please.
Hey guys, so I'm a software engineer, and at the risk of embarrassing myself, I'm gonna talk a little bit about the quantum effects, the physical quantum effects. You probably heard them today, but I'm just gonna talk about the basics that are important for our talk later on. So the quantum effects that govern the quantum computers are more than three, but I'm gonna say the most important ones. The first is the uncertainty principle. This means that you cannot know everything there is to know about a quantum system, so there must be some unknown, so we deal with probabilities. And what's worse is that this can be negative probabilities. Actually, they can be complex, but negative is weird enough for our talks. So negative probabilities or complex can interfere. You can have a positive probability for an event and a negative probability, and they will cancel each other out to give a zero probability for that event. And lastly, I'm going to mention the measurement update. This means that once you measure a property of a quantum system, the value you measured has 100% probability, which means it's certain, and all others go to zero. The probability for all others goes to zero. So now, how do we use these principles to build a machine that does computation? We use the qubit, which is the simplest system that displays these properties. So, like a bit can be a zero, can have a state 0 or state 1. A qubit has a probability of being in state 0 or in state 1, and these probabilities can be complex or negative. So those brackets that you see at the top, 0 and 1, is just a way of signaling that we're talking about quantum states. So now you can measure a qubit, and in this case, there's a high probability that the qubit will be in the 0 state, and then it updates to 0. And there's a smaller probability just because in my design here, the red segment is smaller in dimension than in length than the blue segment. It has a smaller probability of being 1. But in those rare cases, or rarer cases, it will update to be 100 with certainty in state 1. So in order to find out the state of the qubit initially, we need to do a lot of those measurements and deal with the statistics. So importantly is how qubits combine with each other. Two qubits form a quantum state that holds 4 probabilities, 3 qubits holds 8 probabilities. 30 qubits we can have a quantum state that probably fits in a laptop, and 80 qubits will go to the order of the number of atoms in the universe. So it grows exponentially. And like I said, probabilities can interfere, or quantum states can interfere, and they can cancel each other out. So the goal of a quantum algorithm would be to make the probabilities for the state that represent the right answer for a problem interfere constructively and build up, and all the others, they should interfere destructively and cancel each other out. So we manipulate qubits using gates, and these are analogous to the gates in Boolean algebra. I'm just going to mention 2 gates which are important for our talk later. Maybe most of you know the X gate, which turns a qubit in state 0 to state 1, and a qubit in state 1 to state 0. And the qubit in a random states, for a qubit in a random state, it just flips the probabilities of being in state 0 with the one being in state 1. And I'm going to mention the measurement gate, which tells the backend to measure the qubit and give us the results. And afterwards, the qubit will be updated as per the measurement update principle. So a typical quantum algorithm is encoded in a quantum circuit, which typically starts in state 0 and finishes with a measurement, so we get our results out. Now, there's lots of ways to make a qubit, and we don't know yet which technology is going to win, which is the best. But we mostly focused on superconducting circuits, and I'm going to just touch on a little bit on them. So these are electrical circuits that are cooled to really low temperatures, and they have energy levels. And the engineer just isolated the bottom 2 energy levels to access the qubit. But keep in mind that there are higher energy levels, because this is going to be important later in our talk. So how do we use a quantum computer? These are expensive and sensitive machines, so you won't have one on your desk anytime soon. We use them via web APIs. So typically what you would do to run a quantum algorithm would be to encode that in a circuit, optimize the circuit for the backend, send it to the backend. There it will queue until it comes time for its execution. This queue can vary. They can be hours, or they can be minutes, and then you get your results after the execution. So how do you build a circuit for your algorithm? You use one of these meta programming languages that are mostly built on top of Python, not all of them. And one of the most popular is Qiskit, endorsed by IBM. So why would anyone attack a quantum computer? What would they have to gain from attacking it? So one of the basic things that they might want to do with an expensive system is to make it unoperational, like a denial of service attack, or they might just want to target a specific user and disrupt the operation of that user or of that job. Maybe they would want to steal the circuits or steal a quantum circuit. So this is, if you know what's being researched and what is being executed, and you have the quantum circuit, you may be able to reverse engineer and find out information about the research behind it. Then somebody might want to steal the results. Of course, by themselves, these are just numbers. But if you know enough about what circuits are running and what's being researched, then this might give you a really good advantage. And finally, somebody might just want to hijack other people's sessions and use other people's credits to do their own computation. And I'm gonna give it back to Adrian to talk us about the threat models and attack vectors.
Thank you. So, after this introduction, let's switch to what exactly we did. So, as you maybe noted from Sorin's explanation and also from the other talks before, using quantum computers suppose using classical infrastructure, quantum user computer, cloud services, and finally reach the quantum computers. So we try to analyze all this infrastructure, the entire workflow, starting from the end user computer up to the quantum computer and back, just to see where there are possible weaknesses and vulnerabilities. But before doing that, of course, we investigate, or we research the existing literature, we analyze this infrastructure, but we noted and started from the fact that, as I mentioned actually at the beginning of this presentation, that quantum computers are possible weapons, but also possible targets. And because quantum computers could be accessed and used, and they coexist with classical computers, actually in practice there is a combination of both these computing resources, which could be used both by attackers and they could be also possible targets. So an attacker, for instance, could use a classical computer to attack a quantum computer, or could use a quantum computer to attack a classical one, or a combination of both of them. And we try to make a classification of all of this, and that results in this table of 4 categories. You can note the weapons, we can note the targets, both of them in the realm of classical and quantum, and we can have consequently classical on classical, classical on quantum, and quantum on classical and quantum on quantum. Maybe a little bit simplified because, as I told you, there could be some combination of them, but that's just enough for us to try to classify all the possible attack vectors and models that we found in the literature, and also try to imagine by ourselves. In classical on classical, which exists before quantum, also in particular for us refer to an attacker using classical computing resources to attack the classical part of the infrastructure which gives access to the quantum computers. And similarly classical on quantum and the others, as I mentioned before. Along the way we tried to develop possible attacks, some proof of concept attacks, and we succeeded doing that in the 2 categories, classical on classical and quantum on quantum. And I will talk about the first category, and Sorin will talk later on about the second one. Okay, during our investigation and development of our proof of concept attacks, we were restricted by the existing terms of use regarding the cloud services and quantum providers. So because of that, not to break those terms of use, our attacks focused mainly on the end user computer, in particular focused on the SDK used by the end user, by the quantum end user. And also we focused on attacking the quantum computer, but just running as a regular authenticated user using the documented public API. Now, let's see in the classical on classical, which are the attacks that we derived. Now, there are many possibilities, but we try to simplify a little bit the attack model just to be able to focus precisely on the quantum aspects. And in our attack model, we consider that the attacker has some kind of control on the end user computer, being able to run malicious code, the current user privileges, just to be able to interfere with the user processes and data. In particular, you'll see we were interested in being able to read environment variables processes or the files which are related to the quantum SDK. Alternatively, if you do not want to have such a powerful attacker, we could consider that the attacker is able to compromise some SDK, and that SDK is downloaded by the user themselves on their computer. Okay. Starting from that, we try to see which are the possible problems. What I want to mention here is that We use Qiskit, we use IBM quantum platform, IonQ quantum platform, but our findings again are not particularly only to that SDK and quantum providers. Good. First attack, the first problem that we noted is about the API authentication tokens, which are tokens used to let our programs authenticate with the cloud services, which give us access to the quantum computer. What we noted regarding those tokens is that in the cases we investigated, they are generated and provided in clear text. Even worse, they could be stored in the code. Okay, we noted that for the IBM platform, quantum platform, for the IonQ, there are some small differences between them, but the idea is the same. So the first bad thing that could happen is that the SDK allows the user to store that clear text API token inside the code. And that leads to the classical problem of having secrets hard-coded. Once the code goes public, so does that secret. So that's not good at all. Okay, the SDK allows the user, the programmer, to save the API token in some places, not to be directly in the code. One alternative is to save it in a file. That's for a particular, for instance, for the IBM quantum platform. But that file is in a very well-known location. The file structure, which is the JSON file, is well-known. And again, the token is stored in clear text there. Alternatively, SDK allows the user, the programmer, to configure environment variable and store there the token. There are different environment variables for IBM and for IonQ, but finally, again, the token is stored there in clear text. So in our particular threat model, if the attacker is able to control the user computer, it's very easy for the attacker to read the environment of a process, to read the files where the token is stored and steal it. Once that token is stolen, the attacker could impersonate the victim user without any problem, just because the token could be used as it is. Now, impersonating the user means that the attacker, for instance, simply run his own circuits to consume the victim's quantum credits, or maybe looking at the circuits that the victim user run before and their results. We try to see if that is possible to be done programmatically, and we saw for the IBM, for instance, that there is a documented API to which allows the attacker, in that case, to download the circuits and the details about them for the victim. Similarly for the IonQ, but there is no documented API for that. We tried to see that we could discover it, and we discovered it very easily, just because when accessing the dashboard, the web-based dashboard, which allows the user to see the history of his circuits, and when we looked at the traffic, we discovered the API, and we'll write a program to use that API and get the victim's circuits. Okay, which are the defenses, okay, regarding that problem? First of all, something which is the responsibility of the end user is not to store the API token inside the code. That's basic. Secondly, if possible, try to keep those tokens encrypted, decrypt them only when really needed in the application when needs that token. And also, if possible, enable multi-factor authentication mechanisms just to deny the attacker being able to use the token if the token were stolen. The other problem we investigated were related to the quantum circuits. We wanted to see if the attacker is able to interfere with the quantum circuits. Again, our attack model supposes that the attacker is able to compromise the SDK, and we investigate a little bit which parts of the SDK could be compromised by the attacker. Once that SDK is compromised, the attacker could steal, so could interfere with the entire workflow of sending circuits to the quantum computer. So interfering with that mechanism could steal the circuits or could change them, maybe injecting malicious gates or malicious additional circuits. We developed an attack like that and tried to harden a little bit the job of the attacker. So we suppose that, okay, the attacker is able to run some malicious code but has no idea of where the SDK is located in the file system, because indeed it could be installed in different places. Okay, but we know that Qiskit SDK is based on Python. So the attacker could monitor all the processes of that user, trying to identify only those running Python, based on their command line details. Once those processes, Python processes, were identified, we have to filter out those not using the Qiskit SDK, which is again possible looking at the environment of those processes. Once we identify which are the processes using Qiskit SDK, we know precisely where that SDK files are, and we try to corrupt them. And we try to corrupt the SDK. We have to identify which are the files and functions which are used to manipulate the transpiled circuits. So not those which are designed and visible by the user, but those which are to be sent to the final quantum computer. It was very possible because the transpilation actually transpiles the circuits in a language which is understandable and could be manipulated. An OpenQASM, which was mentioned in the previous presentation, so it was very easy for us to inject additional malicious circuits, or it was also possible to corrupt the intercepted ones. Okay, here is some details about which functions we change to intercept and modify the circuits. And there is an example of an injected circuit which is in OpenQASM. It had to be transformed a little bit, but it was really simple to do that. Which are the possible defenses against that? First of all, again, something which is dependent on the end user. Try to not take untrusted SDKs, because they could be compromised. If the source is trusted, try to check if the integrity of the SDK is preserved. Something which is not necessarily the responsibility of the user, but maybe on the SDK developers, is to try to create an environment which cannot be interfered with even by a local attacker. Like, for instance, configuring a security solution to monitor for the integrity of the SDK files, or trying to run the SDK processes in a trusted, isolated environment like Intel SJ enclaves or something like that. Okay, that was the part regarding classical attacks on the classical part of the quantum infrastructure. Now let's move on something which may be even more interesting, quantum over quantum, and that's the job of Sorin, and let's switch back to Sorin.
Okay, so how do we use quantum effects or quantum computers to attack other quantum computers? So the first thing we did is research who else has thought about this and if there's any literature about it. So it turns out that we found a handful of papers talking about this, but most of all were talking about a regime that is not possible today. So the idea behind all these papers, which refer to both superconducting and ion traps technologies, is that queue times, as I said, are really long and really annoying. So if you have a big enough quantum chip and the user doesn't use the entire chip for their computation, you can fit multiple users' programs at the same chip at the same time. And of course, that would lower queue times and will make the usage of the quantum chip more efficient, but it will open up a can of worms in terms of security and interference between users. So we tried something else. We wanted to find something that's accessible or possible today, and we mostly looked at errors. qubit errors, gate errors, measurement errors, and we focused on the reset operation. So the idea is that if everybody queues up their jobs to be run on the quantum circuit and the reset operation is not good enough, then an attacker can just read the qubits, just measure the qubits without doing anything else, and they would read the results of the previous job, of the job that ran before them. So imagine if you run a company and have multiple scientists and you want to simulate a molecule that's promising for discovering a new drug, and you put together a team of scientists, engineers and all that, and then your competition just runs a job after you and gets all your results. If they know a little bit about what you're researching, then all your competitive advantage is out the door. So we wanted to see if that's possible, and we started on a small scale. We used IBM Osaka, which has 127 qubits, but we isolated the first 7, and we looked only at the first 7 qubits because of the limitations. We know that so the shot count limitations was the most important one, because 7 qubits can hold 128 different patterns of zeros and ones, and in order to get good statistics, we would need 100 data points for each of these patterns. So we settled on 19,000 shots per circuit or per experiment. So how did we design our experiment? We had first a victim and then an attacker. And on the victim side, we just had to prepare a pattern of zeros and ones and then measure it. And this is to simulate somebody doing a really complex algorithm that ends in a measurement. And then on the attacker side, the attacker just has to measure the qubits and see if he can infer anything about the pattern that the victim had. So we started, we take a 7-bit long pattern of zeros and ones, and then we create a circuit for the victim that prepares the pattern and measure it. We create a circuit for the attacker that just measures the circuit. We bundle that in a job and send that for execution 20,000 times, and then get the results and interpret it. So for the results, we get the statistics from the victim, we get statistics from the attacker, and then see if the attacker can so compare the two patterns and see if the attacker can recover anything about the victim's pattern. So our results were not good at all. First of all, because we were a little bit naive in our initial design. Qubits are independent, so looking at patterns like this is not a good way to do it. And we handled a lot of we had to deal with a lot of measurement errors. So in many cases, the victim didn't even measure the pattern that they had prepared because of measurement errors. But even if we threw those cases away, the attacker did well on some patterns, really bad on other patterns. So we couldn't decipher anything about this. So we started over, and we said that, first of all, we need to deal with measurement errors. And the most important measurement error is the probability of measuring 1 when the qubit is actually in state 0. So this is a measurement error. And we know that this is the defining error that that the attacker would face. So in the ideal case, when the reset operation is perfect, or if there's no information to be leaked from the victim to the attacker, then the attacker would only measure a 1 because of this error. So we designed an experiment to find out what this error is and if it matches what IBM reports as this error. And we used the same setup as before, but this time the victim had prepared only the 0 pattern. So in this case, there is no information to be leaked from the victim to the attacker. So on the attacker side, all the qubits should actually be in state 0. And now, if the attacker measures a 1, this is because of the error that the probability of measuring a 1 if the qubit is actually in state 0. So we did the experiment and computed the probability of the attacker measuring 1, and these are our results. The yellow bars represent what IBM reports as the probability of measuring 1 when the qubit is in state 0. And the blue marks, the blue axis, is what we computed as the attacker's probability of measuring a 1. And we can see that they are pretty much aligned, accounting for a statistical error, of course. And this tells us two things. One is that what IBM reports as this error is correct, and that we are also correct in our assumptions. So we are on the right track. So now if we go on with an excited state experiment, we know that anything, so when the probability increases for the attacker, this must be because the victim had a 1 on that qubit. So we design another experiment, which is the excited state experiment, where the victim, so we're using as the same setup as before, the victim now prepares the all 1 state, the excited state, on every qubit. And now we note what the attacker measured, and we hope to see if the reset operation is imperfect and data is leaked from one job to another, we should see an increased probability of measuring a 1 on the attacker's side. And these are our results for the two experiments together. So all that bundling of jobs and executing 90,000 times, we did that 16 times for the cases when the victim prepared the 0, so for the baseline experiment, and those are the blue marks. And the red marks are for the excited state experiment where the victim prepared the 1. So first of all, we can see that most of the red marks are above the blue marks, which means that there is an information leak from the victim to the attacker. In some cases, like qubit 5 and qubit 6, there's a clear divide. There's actually a gap between those cases. On other qubits, like qubit 4 or qubit 0, there's a lot of overlap, which means the reset operation is really good on those qubits. So armed with these results, we can have a detection model, or the attacker can have a detection model, which is just a threshold. And the attacker can use this model and say, okay, I'm going to get statistics and compute my probability of measuring a 1. And if this probability is above the threshold, I'm going to assume the victim had a 1 on that qubit. And if it's below, my probability is below this threshold, I'm going to assume the victim had a 0 on that qubit. So the threshold is different for every qubit. And armed with this model, we remade the initial failed experiment. So prepare a random pattern, run attacker just measures, and then interpret the results according to the threshold, and see if we can recover anything. And using many random patterns of 7 qubits, we could compute an accuracy for our model. And we can see that the model did really well on qubit 5 and qubit 6 as expected. Qubit 6, just because there was a large gap there, did actually great, 100% accuracy. But on qubit 0 and qubit 4, the model did not do so well. I should mention here that the worst the model could do is 50%, because that's just a random guess. So we were pretty happy with what we have discovered, but then Adrian here, who is our cybersecurity expert, said that, okay, just from this data, there's a better experiment or a better attack that someone can use. Let's just flip the victim and the attacker, and now have the attacker just prepare the 1 state, and then there's gonna be information leakage from the attacker to the victim, and the attacker can inject noise to the victim circuit. And remember that there's a promise, or the quantum computer has a promise that the qubits will start in 0 when you start your computation. And if information leaks from the attacker to the victim, then there's an increased probability that the qubits will not be 0 at the start of your circuit. So it's like having an X gate there. It will mess up all your computation. So in the case of so this would be the design of the attack, where the attacker prepares the all 1 state and measures, and then the victim is not sure whether they start in the 0 state or not. So in the case of the team that researches the novel molecule, Now the competition doesn't want to steal the results anymore. The competition has their own team and their own computation. They just want to delay this team, and by using this fault injection attack, that they can mess up not all but some of the experiments of the team, and they can delay the research. So these conclusions come from the same data. We don't need to do anything else, just reinterpret the results we got before. But there's then actually a way to do it better, to enhance the power of this attack. Remember that I said that there are higher energy levels, and we can use a pulse level program to raise the energy of the qubit to the second excited state. And in this case, the attack is way more powerful if the attacker raises the qubits to the second excited state. Now we have the green marks, which are superimposed over the results we have previously. And now we see that almost on all qubits we are close to 50%, which is total randomness on the victim side. So the victim has no idea whether their computation will start with a qubit in the 0 state or in the 1 state. So we did this for 7 qubits. Does it all work for the entire qubit, the entire chip? And it does for IBM Osaka. So we see that this is a behavior across all the qubits. And maybe there's just a problem with this chip. What about other chips? So we also tried it on another quantum chip with 127 qubits, which is IBM Sherbrooke. And we see that the behavior is the same there too. So now I should mention some limitations, because this attack looks really powerful, but we did make some assumptions that are not really exploitable. So that makes the attack not really doable right away. So first of all, when you run a job when 2 jobs run one after another, is that one job runs all the shots, and then the other job comes and runs all its shots. So in our experiment, we interleaved the attacker and the victim, and on every shot of the victim, we had the shot of the attacker, and then so on both the readout experiment and the fault injection experiment. So there are these limitations and these assumptions that we made, but even so, if the attacker is determined enough and the victim does multiple job runs, there could be some influence that the attacker can use either to read the data or to inject faults. And there's another assumption that we made here, is that the reset, so we bundled everything in a job, and we assume that the reset between multiple circuits in the same job is the same as the reset between jobs. And we reached out to IBM to ask, is our assumption correct? And they said, no, your assumption is incorrect. The reset between jobs is perfect. Okay. We asked, okay, how long is it? Can we test it? And they declined our request to test it. So maybe they'll change their mind, I don't know. We'd love to test that. So moving on from the way we attack, so we use this attack, how do we defend against this attack? So it's not straightforward. There's 2 ways of doing a reset. One is the active reset, like you measure the qubit, and if it's in 0, you leave it in 0. And if it's in 1, then you flip it to 0. This will be an active reset. But this is prone to errors, measurement errors, and gate level errors. Or you can leave the qubit to relax on its own. The qubit is governed. The qubit has the T1, which is the time it takes for it to relax naturally from state 1 to state 0. And you could just leave it for a number of T1s just to make sure that the qubit relaxes. So what we did is add delays between our circuits to see if that's the case, if that helps in any way. So this is just a base level experiment on the entire IBM Sherbrooke quantum chip. And this is our initial results with no delay between circuit runs. Now we added a T1 delay, and we see that we can still detect an increase in measuring a 1, an increase in the probability of measuring a 1. And then we added the maximum delay that the backend allowed for, which is approximately 3 T1s, and we see that the probability decreased even further, but it's still detectable. So maybe at 5 T1s it will work. We couldn't test that, but it is a solution, but this would make everything run slower and the queue times would increase. I don't know, there may be better solutions. Who knows? So we have only scratched the surface even with this attack. We sure would want to try this on ion traps. We know ions are reused between circuits. Does this work there too? There are other quantum chips, superconducting chips that we want to try it on. And there are a lot of attacks that can be done or can be researched. So I think this is up to the entire community, to you guys, to help find better ways to use the quantum computer and to defend them. Thank you. If you want to know more, on the QR code you'll find our paper, our white paper, or come talk to us after. Thank you.
I love that we've managed to get a quantum computing company to show us how to build a quantum computer, and then we got some quantum hackers showing us how to hack that same computer. I think that's brilliant. Huh? Oh, there it is. Okay, everyone, are there any questions? Please do come forward if there are. Because the microphone's here, sir. If you want to queue up for any questions, do it here.
Hi. So it's kind of like two parts. So on the two methods that we sort of talked about. So in the classical versus classical, if you've got control over a system, why not just monitor network traffic and change the results as they come back, or deny them completely? And then for the quantum versus quantum computers, you mentioned that this was done job after job. Was it done from separate accounts, or was it the same account that was used for it as well?
So this was done inside the same job. So inside the same job, we ran the victim and attacker circuit one after another, not in separate jobs. So one job, it means it's the same account.
You are right. If the attacker controls the computer, could done anything actually. But that's why we tried to compromise the SDK to interfere with the circuit after the transpilation. Okay, just imagining that maybe somehow on the channel the attacker is able to intercept those circuits, and our question was, it is possible to interfere with them after being transpiled. Okay, and the idea is that it's possible. They are transpiled in the QASM, open QASM, which is well known. They are also serialized in some way, but this serialization process is very simple. There is no encryption there, just an encoding in base64, something like that. So that's what our focus actually.
Brilliant. Other questions? If there are no other questions, please give it up for Sorin and Adrian again.